what I would now like to talk about in the rest of today's lecture is about the Leray flow. So you can put like this. So Leray flow, it's near the junction. So we introduce the following notation, more notation. So G epsilon is omega epsilon 0 union with the big union of G epsilon I. So this G epsilon I will be x1I. So this is important to introduce, that you have, you will introduce a solution in this area near the junction and prove that, you will not prove, you will just say that there is a proof of the exponential decay towards the Poiseuille solution. So that's the basic idea. So x1, x star I from omega epsilon I where so x1 is from 0 to minus d epsilon ln of epsilon. So this is an important value. You also have this notation, so G is the union of 0 to m omega I, where omega I is y1, y star I from R3, y1I, y star I from BI. Okay. And now the idea is, if you remember, it's a similar idea as when you had the Leray problem for the boundary layers at the left or right hand side, at the left end or right end for the three-dimensional undeformed pipe. So you introduce this, the first variable in all three directions. So V epsilon is epsilon squared V of x over epsilon. This is the rescaling in all three variables. And Q epsilon is epsilon Q x over epsilon. So you plug this in 1, 1. So this is with the first variable. So epsilon is x over epsilon. We have the following, so minus Laplace V plus gradient Q is equal to 0 in this G. And then divergence of V is equal to 0 in G. V is equal to 0 on border of G, and you have this asymptotic condition. So as y goes to infinity, basically y1 goes to infinity, but okay, you have that this is equal to u1, which is vi y star I over li. So what this means is that as you move away in any one of the pipes, basically you have the convergence to ui. it will be shown that this exponential decay towards this Poisson solution, as I said, can be obtained. So let's look like this. So this is 7. So problem 7. As I said, is called the Lie raised problem. Okay, so there exists a unique solution. For any choice. So for any choice of pressures, Pi. Okay, so moreover, we have the exponential decay. So I will write down this result a bit later. But let's first comment on the matching, which is important. And then from this exponential decay, you have this error that comes from matching will be small enough in order to satisfy your error estimates. So in some way, you need to match this, as I said, solution inside the junction and the Poisson solution. So you have these two. So we have epsilon of x is epsilon squared v of x over epsilon, and q epsilon of x is epsilon q of x over epsilon. So this is the approximation. Near the junction, as we mentioned. And far from the junction, so u epsilon I, u epsilon I is the Poisson solution far from the junction. So we put like this in this omega epsilon I. So there are a lot of these domains that have similar notation, but I hope you can manage in all this. So x1 I, x star I, in omega epsilon I. So we had this layer up until minus d epsilon ln epsilon, and you have this other part of the pipe. So from minus d epsilon ln epsilon to Li. So these two solutions as I wrote down the Lie problem, it says that these two solutions match asymptotically. As epsilon goes to 0. However, they do not match on this interface, which is given by minus d epsilon ln epsilon. So do not match. Do not match on gamma epsilon I, x1 I, x star I. So this interface given by minus d epsilon ln epsilon. Okay, so what do you do with this? We can write in this form. So we have that v epsilon is basically we can write it in this form, so u epsilon I plus some e epsilon I, which will be small enough. So it's given by e epsilon I is epsilon squared v of minus d ln epsilon x star I over epsilon. Okay, let's put here minus ui of x star I over epsilon. Okay, so now you want this e epsilon I, this error, let's say, to be as small as possible. So now I mentioned the result from Galdi's book, so result in the exponential decay. I think it comes from the, basically from this exponential decay result. Somehow it, in some sense, this plays an important part. Okay. I didn't check precisely why this, but I know I asked also this Professor Fajan, and I think it comes from the naturally when you look at these exponential decay result and this interface. Okay.
Yeah, because when you try to construct the match, when you try to match near the junction,
Yeah.
It's not really natural to, how to say, wonder that this should be the power, the neighborhood of the.
Yeah, I know what your question is, but I think it comes. I can check in the proof. I'm not sure, but I know that it disappears regularly. So. Okay, so what you have is v epsilon minus u1 y star I plus gradient v epsilon minus gradient u1 ui y star I plus the pressure is determined up to a constant. So you have this q epsilon minus pi minus q over li. So this also, I think, is called a stabilization constant. So this is less or equal to c epsilon minus tau y. So here tau is bigger than 1 or equal to. For each y in gi, which is basically g epsilon I, which is rescaled by 1 over epsilon. And g epsilon I is exactly this. Your question, it's defined as up until minus d epsilon ln epsilon. So it appears somehow in the proof, this exactly how. we can check in probably it's in Galdi's book. It needs a bit of just adaptation, but it appears.
Probably, yeah, I get it now. When you start going to the proof, probably this V you have to substitute it and somehow to cancel with the ln.
Yeah.
E to the power something.
Yeah. So this appears in, I think, in all problems of this form. You have this sort of interface. So maybe also in our problem it could be.
Yes,
it could be the. I know. Yeah.
Yeah.
Maybe this could be the case also. However, this is just a digression. The problem that we were talking about is that basically somehow the junction is of order epsilon squared, and the pipes are order epsilon. Here the junction is of order epsilon. So probably, I'm not sure if this would definitely change things, but up until now I'm not sure how much. So. Okay. Anyway. Now you think from this that we'll just finish this up, this last couple of ideas. So E epsilon I is less than equal to C epsilon B plus T. Okay, so this is this, let's say, error. And what you also need to check in order to define the correction for this estimate. So you have the integral over the interface, E epsilon I times E1 I. So it's epsilon squared over BI, integral over BI. So we have V of minus D ln epsilon Y star I minus UI Y star I Okay, so this can be computed to be 0. So why is this important? Well, then you have the necessary compatibility condition for your correction, which will be done as, which will be given in more or less standard form, in this form. So we define the correction. So it's a solution not necessarily unique of the divergence equation given in this form. So divergence, so you can denote this by 9. Divergence of H epsilon I is 0 in V epsilon I, which is the from minus D epsilon ln epsilon to the end of the pipe. H epsilon I is minus 1 over epsilon squared E epsilon I on the interface, and H epsilon I is 0 on V epsilon I without the interface. Okay, so since we have the compatibility condition satisfied, so we have a solution. It's not unique, but that's not that much important. So we have a solution due to the compatibility condition 9. Okay. So you now have basically everything to define your synthetic approximation. So let's write this down. So we define the asymptotic approximation as, so the epsilon, we denote it approximate, is epsilon squared Q epsilon approximate. So you have like this, Q epsilon approximate. So it's V of x over epsilon in G epsilon, so in the interior layer near the junction, and U epsilon I, so this is the calligraphic U epsilon, plus the correction, which will improve your estimate, and V epsilon I, so it's in the rest of the pipes until the end. For the pressure, it's not a problem, so we have P approximate is P epsilon I in V epsilon I and Q epsilon in the layer near the junction. Okay, so this is what I wanted to talk about today. Of course, now you will have the proof of the error analysis, which carries quite some technicalities, but there is not, regarding these main ideas, there is not much to be, I would lose maybe 2 hours on it, and you would not gain much about it. So you can check about it in the paper. Okay, so you have any more questions regarding this today, or is there anybody online, or no? No, okay, bye everybody online. Future watchers. Okay, next week we continue with micropolar. We will have two lectures on that because I will go into some more details. Thank you for